Hi everyone. This paper on contextualisation of DFDs for security analysis is joint work that arose from discussions about metrics for software security at a Dataflow seminar last year on empirical evaluation of secure development processes. Now in this work, we're specifically motivated by metrics and the ability to reason about high-level design models created very early in design processes. And our big idea is that we don't need to trade off the simplicity and expressive power of these models if we can put them in context with other models. So the focus of our paper is the data flow diagram, a simple but expressive modeling notation for modeling the flows between entities, processes, and data stores. It's a well-established system analysis technique and one of the more popular techniques for threat modeling in general. It's an easy notation to pick up, but the limited semantics makes reasoning about them difficult without augmenting them in some way. But doing this weakens the very strength they have as a boundary object between different threat modeling stakeholders. But as the title of our talk suggests, rather than augmenting DFDs, we could leverage the idea that DFD nodes can be put in context by different model elements. And by doing this, we can reason about possible issues in DFDs that would otherwise be invisible. To see why this is the case, let's look at a meta-model of related design concepts. So this class diagram is a subset of the CAIRIS meta-model, which we refer to in the paper. The class diagram shows a conceptual relationship between design concepts and requirements engineering in grey, usability engineering in blue, and security engineering in red. Now we can see that processes are abstractions of use cases, which are a requirements concept. And a use case puts in context a more qualitative task description, which is a usability concept. We don't assume that there is a generic designer who is listing or specifying these model concepts. The models associated with the concepts could be produced by different teams at different times. But because of these conceptual links, we've got a means for reasoning about the impact that usability models might have on security models and vice versa. To see how this works in practice, we've considered how contextualization can help us spot tainted data flows. Now, taint flow analysis is a well-established technique in computer security, and there's also been previous work looking at how this might work for DFDs too, but that requires changes to DFD semantics. Our paper presents an approach where human error sources act as taint sources before and after any data flow processing takes place. Although DFDs are graphs, a DFD is also a set of data flow types, where a data flow object is composed of a label, names and types of nodes where data flows from and to, and although invisible in diagrams, also a set of data items carried by the data flow itself. Based on this definition of data flows, the first step of our approach is to turn the DFD into an array of unique data flow sequences, where the from attribute of the first data flow in the sequence is an entity. This is summarized by the algorithm in this slide, which is described in more detail in the paper. With this array now constructed, we enumerate the data flows in each sequence and log potential pre-process and post-process data flow taint. Now, pre-process taint arises when opportunities for human error and violations are present. And as the conditions in this slide and the paper show, we rely on other models for context. For example, we're relying on tasks that put processes in context, and attackers and personas that put more abstract roles and human entities in context. Now, post-process taint arises when exceptions from processes impact information flowing from these processes. Now, in this check, the process itself provides context for other models, particularly requirements models. For example, system goals are operationalized as processes, where exceptions to these processes obstruct one or more of these goals. In parallel to this, we also rely on the relationship these elements have with assets of value. In other words, assets associated with obstacles that are carried by these outgoing data flows. Our intention is that, provided you've got the necessary models, the approach described should be automated in the form of a suite of model validation checks. Now, to show you this is feasible, we've implemented these checks in CAIRIS, which is an open source software platform for listing, specifying and validating secure and usable system specifications. Because it was developed as an exemplar for the ARIS meta model partially seen earlier, it supports all the concepts necessary for our approach. Now, the graphical models you see in the presentation in the paper are automatically generated by CAIRIS based on declarative data processed by Graphis and rendered as SVG. And CAIRIS' model validation checks are implemented as stored procedures within the SQL-based CAIRIS database that stores the elements and relationships of a given CAIRIS model. Now, to implement this approach, we made no changes to any pre-existing visual models or the ARIS meta model. Now, to illustrate our approach, we've used it to spot process taint in the specification of a software repository for telemetry software used by a water company, which, although fictitious, is based on a real organisation. Now, for those of you who don't know, telemetry software is used to monitor and remotely control clean and wastewater infrastructure, things like pipes that are connected to outstations. Now, as part of the specification, we have a persona which is called Barry, which was created by human factor experts to represent instrument technicians. We've also got a task narrative describing how Barry might modify a telemetry outstation. Now, there have been some well-publicised examples of what happens when these outstations are maliciously tampered with. But given the duress instrument technicians making software changes might be under, we'd like to see the impact that this fatigue might have on Barry in this task. Now, how the specification was created is not the subject of this paper, but if you look at the references in the paper, you can get a bit more information about how it was created. Now, but as you can see in the slide, we have made the pilot study CAIRIS model available for those that want to inspect it in more detail. Now, in this slide, we can see the DFD associated with telemetry software modifications, with the bottom left table showing what information is carried in each flow. Now, if we run a model validation check, we're going to instantly complete steps 1 to 3 of our approach, but we're going to break this down to see what's going on, starting with step 1. And we can see from the bottom right table that the results of generating the dataflow sequences is a dataflow sequence array of 5 elements. And to give you a preview of what's to come, we can also see that pre or post-process taint flow checks have failed for the first 4 of these elements. Now, the DFD alone doesn't explain why the pre-processed taint flow checks failed, but if we look at the results from step 1, we can see that all the sequences are prefixed with a job data flow, and this contains job information. And that information also happens to be used in the outstation update task that contextualizes the process. Now, we can see that Barry persona interacts with job information, but Barry isn't the only instrument technician here. We can see that this role is also shared by our attacker who, while not malicious, happens to be resource constrained. And that role also corresponds with the entity that's the source of the job data flow. And on inspecting the task, we can see that Barry finds this particularly demanding. Now, the check doesn't tell us what human error might occur, but it does highlight the need for more investigation about what could be tainting the data flow. So it could be that Barry picked up the wrong job info for the right outstation, or maybe the right job info for the wrong outstation. The DFD alone does not explain why the post-process taint flow check fails either, but the use case specification for the process does have an exception we've highlighted in green, and if you look more closely at the obstacle resultant from the exception, we find that it's associated with an information asset, alarm, that also happens to be carried by the alarm data flow outgoing from our process. Now, as to why the exception occurs in the first place remains unclear at this point, but inspecting the broader asset model, seen in the top left of the slide, could be a starting point for investigation. For example, possible problems with the availability of the telemetry network asset could bring us closer to a root cause. Alternatively, we could look again at our outstation update task to spot other reasons for why an alarm might not be sent. In presenting our approach, I hope we've shown that, by putting DFDs in context, we can find potential sources of data flow taint without making any changes to DFD semantics. By indicating otherwise invisible problems, our approach also sheds light on why these problems might exist. Our approach also highlights the potential of leveraging usability models. It's usually the case that such models are empirically grounded and the result of some fairly extensive user research. The resulting user research could yield potential vulnerabilities, so in presenting this work, we want to indicate how human factor experts could play a more active role in threat modeling more generally. One of the nice things about our work is that should you have interoperable tools that together support the concepts we describe in the paper, you should be able to implement this approach yourself. If you're an interested researcher or developer, I hope the algorithms in the paper and the open source CAIRIS codebase gives you enough cues to get you started. Thanks for taking the time to listen to our talk. I hope you found it useful, and please do get in touch if you have questions or want to find out more about our work.